Hi, my name is Terell Cathey. I was given the opportunity to research advanced power systems for deep space missions through NASA's STARRS program. Before I begin, I must add that the material contained in this document is based upon work supported by a National Aeronautics and Space Administration grant or a cooperative agreement. Any opinions, findings, conclusions, or recommendations expressed in this material are those of the author and do not necessarily reflect the views of NASA. With that being said, let's start with some background information. There are three different focuses for advanced power systems. The first is power generation. There are many different sources of power that can be used, such as chemical, solar, radioisotope, nuclear fission, and nuclear fusion. Next, there's power storage, which focuses on providing the highest possible specific power with sufficient durability in the mission environment. Storage is focused further on developing batteries, flywheels, regenerative fuel cells, and capacitors to store the highest possible specific energy with specific durability and, when applicable, cycle life. Lastly, we have power management and distribution. The goal of power management and distribution is to be able to reliably support high-powered electric propulsion into deep space, as well as support operations in extreme environments. The technology I focused on was in power generation. It provides the most significant answers to the two biggest problems in deep space missions. First, being the length of the mission and the health problems associated with them, like bone atrophy due to the lack of gravity and increased risk of cancer due to the increased exposure of radiation. There are solutions to this, but they feed into the second problem with deep space travel, the cost. The cost of the mission becomes extremely steep. For scale, the Mars 1 mission, which is currently being planned by a private Dutch company, estimates that will cost roughly $6 billion for the first manned launch to Mars and $4 billion for each subsequent launch. Fusion-driven rockets could address both of these issues. Rocket propulsion technology can be split into 4 different types: chemical, which is the most commonly used, non-chemical, advanced, and supporting. Chemical rockets are what was most recently used in SpaceX's Dragon 2 launch. They have the disadvantage of having a low specific impulse at about 235. And the energy output of chemical rockets is also low when compared to other types. Of rockets. For example, the combustion of hydrogen and oxygen has an energy release of 13 megajoules per kilogram, whereas nuclear fusion and fission have much higher energy outputs. Specifically, nuclear fusion outperforms this, providing significant increases in specific impulse, which goes up to an estimate of 900 and a higher energy output. The fusion of deuterium and tritium has a 3.6 times 10 to the 8 megajoule yield. For fusion, however, researchers have been pursuing a way to make nanoscaled fusion explosive device using inertial confinement fusion, ICF, which compresses a spherical cryogenic fuel pellet into 3 dimensions. This produces an energy gain of 200. The downside of this method is that it takes an incredibly large facility to ignite the pellet using an array of high-powered lasers. That facility would, in order to be able to actually be able to see it in full, you would have to use an aerial drone to get a picture of it. Recently, however, there has been a new breakthrough method of magnetizing the compressed plasma called magneto-inertial fusion, MIF. This is the concept behind the fusion-driven rocket. In the mid-90s, it was realized that a large magnetic field could be used to suppress the thermal transport and thus lower the imploding power needed to compress the target to fusion conditions, which allowed the use of larger metal shells known as liners to compress the inner plasma to fusion conditions due to the decreased losses of thermal energy over time. This also allowed for the liners to be pushed inward by magnetic fields. Another major discovery around this time, just 1 second, I'm sorry about that. Another major discovery around this time from Bosco showed that sufficiently magnetized plasma would reach fusion ignition well before the restrictive conditions were met. This means that the new method of nuclear fusion could achieve ignition and much lower compression than ICF required. Combining these concepts allowed for a propulsion method that uses the liners as a propellant as well as achieving fusion conditions. Inductively driven thin metal liner is used as a way to convert the fusion energy into propulsion energy. It does this by compressing the magnetized plasma. This shell acts as a thermal blanket that becomes superheated and ionized before expanding rapidly within the divergent magnetic field, which converts the thermal energy into thrust. You can see the concept drawings drawn over here as the plasma is formed and then pushed outward, creating increased energy. They tested this theory by using a Mars simulation. They used NASA's Copernicus software, and which would model the flight path that the rocket would flow through, and they used the stats from the Design Reference Architecture 5 that NASA put out for a Mars mission. The goals of this launch were to have a 90-day transit time to and from Mars, to only have a single launch with a payload mass of 63 megatons, no pre-deployed assets, and to recover the spacecraft so that it could be reusable. These are very important because they directly address the 2 major problems that we have with deep space missions. The important takeaways from this is this mission comparison table down here, where you could see how the fission-driven rockets did compared to the nuclear rockets and the chemical rockets. The fusion rockets were the only rockets able to complete this mission with 1 launch, whereas the other 2 required significantly more, the fusion being the closest with 9 launches. They also had a mission time, the fusion-driven rocket also had a mission time of 210 days, which is excellent compared to the 914 days that the fusion-driven rocket would have, as well as the chemical-driven rocket. And if you include the additional launches that they would make before the manned mission launch, it would be a total of 1,680 days from the start of the mission to the end, which is significantly longer, significantly more expensive, and causes many problems. Over here, you can see the two figures that they came up with to demonstrate their design. First, in the bottom right, you have the design of the actual fission-driven rocket and how that works. You have the shock absorbers, you have the fuel, and you have the liner here that is compressing and pushing out your propellant. All right, here's the liner with the injector and the exhaust over here. Above here, you have the overall design of your rocket with the fusion-driven rocket down here, and all that goes with that. You have the solar panels that will help power the fusion-driven rocket, and you have the lander and the habitat that the astronauts will be in. Now, this is still a theoretical technology, and so the feasibility of the inductively driven metal liner, compression of the plasma to fusion ignition must still be demonstrated. They're currently running experiments at the Plasma Dynamics Laboratory at the University of Washington and at MSNW. These experiments were, the initial results of these experiments were recorded and tracked in multiple graphs, tracking the magnetic field of the liners, the resistance, the temperature, the linear velocity, the linear radius, and the flux of these liners. They were testing to see if the liner model behaved as expected, and they were calculating this using the AEDS calculations. I have included these graphs and right here. And what you can see is on the left is the graphs with the AEDS calculations, and on the right is their actual experiment. Flip that. Sorry. On the left is the experiment, and on the right is calculations. And what these results have shown is that the experiment very closely matches what was expected through the calculations, and proves that their concept could be calculated and measured in such a way. They ran a couple other experiments that also similarly very closely had their experimental results following their calculated results. So the two most significant problems preventing NASA from pursuing their mission directive of advanced power systems for deep space missions is the amount of time it takes to travel out that far and the cost of the mission. This new technology has shown that it can significantly reduce the time it takes to travel to and from one of the deep space missions that we are currently trying to implement, which is the mission to Mars. It can do it significantly faster, somewhere around 700 days faster, and with much less trips actually caused, which will significantly reduce the cost of the mission and make it an extremely viable solution. Thank you.